give him a bouquet as a token of appreciation.
It's me. Thank you very much. Good morning, everybody. That wasn't very upbeat. Good morning, everybody. Good morning. See, I knew you got it in you. Greetings. My name's John Tukey. I'm Professor of Construction at AUT. I'm very proud to be a member of the faculty at AUT. We're a relatively new university. However, we've been an organization for many, many years. I mean, we have a history of about 150 years in New Zealand. We're very keen on educating people for industry and creating the conditions where you guys as individuals coming, whether you study with us or research with us or whatever it is, are actually prepared for industry, and that's our thing. You know, because we have and we feel that there is a great need for individual capabilities and capacities to be able to contribute for the future. In life, ladies and gents, I'm here to tell you, you've got a couple of choices. You can make a noise or you can make a difference. I would ask you to consider, what is it you want to do? Just want to make a noise, or do you want to make a difference? Okay. We're on the same page. Enchanté. Now, the good news is that I'm here to talk about opportunities primarily to be able to make that difference. And one of the things that we collectively as a society can do, as engineers, as architects, as the creators of the built environment for the future, is make a difference. Now, what I'm going to do is go through some of the issues that we have in society in New Zealand. I'll introduce you to some of the things in New Zealand. You might even be interested in coming along and studying with us. Oh, go on then. We'll take you, because we love you. But it's a great opportunity. There are some really interesting problems that we have to deal with in New Zealand. I'm going to introduce some of the solutions that we use, some of the solutions that we're adopting, and I'm also going to introduce some of the bigger issues that are going to affect India, South Asia, the world going forward. Okay? That's the plan. We're going to do it in about 35 minutes, and then you can ask me some Q&A. Everybody happy with that? Excellent, you see? You're already buying into the Kiwi worldview. I like it. Okay, so first things first, let's talk a little bit about the current situation. This is pretty much standard. I'm not sure how well you can see the photograph on the right-hand side there. A bit of real estate post cyclonic flooding in South Philippines and so on. Ladies and gents, this is becoming the norm. It's becoming the norm because what we're seeing is increasingly energetic weather events associated with climate change. Now, it's interesting when we talk about climate change. I'm older than you are. Hard to believe, but true. I am actually older than you are. Back in the 1970s, when I was growing up, and I was the same age as you, I was told that there was going to be a forthcoming ice age. We started buying jackets. We thought we were going to be freezing to death because it was going to be an ice age. Scroll forward to the 1990s, all of a sudden it's global warming. Get out your shorts and flip-flops because we're going to be by the ocean, it's going to be sunny, lots of sun, it's going to be dry. Scroll forward to the early 2000s and to this day, all of a sudden it's climate change. It feels as though they're hedging a bit. You know, we're not sure if it's going to get warmer or colder, it's just changing. Oh, okay. But this is what we're facing at the moment. What there is an awful lot of competing evidence. What there is a lot of people playing politics, trying to convince you guys and your age group that the end of the world is nigh or not, okay? I'm just going to go through some of the sort of primary features, and we can talk about the implications going forward. The long story short, is that we're in a bit of a state of denial. We tend to carry on doing the same now as we've always done. And that ultimately is not going to happen. Now, if we look at the basics, we can go back to about 1938-39 when the first research was done associated with carbon dioxide concentrations in the atmosphere. That was a guy by the name of Guy. That was a guy called Guy. And Guy Callender, he identified the fact that there was various sort of indicators of the increase in carbon dioxide concentration. Now, you can see this as a result of things like tree rings, dendrochronology. You can actually see the increase in the thickness of growth patterns during the latter years since the 1700s as a result of climate change. And basically, this guy dude, he was postulating the idea that, there's an increase in carbon dioxide that would lead to an increase in the amount of wood deposited during growth periods in the cycle of growth in trees. Nothing much happened. A little thing like the Second World War kicked off. All of a sudden, people were more interested in killing each other and burning oil stocks and God knows what else rather than actually making a difference. Scroll forward to 1958, all of a sudden we started to see quite significant research that was taking place primarily in the States, in Hawaii, by this chap by the name of Charles Keeling and his PhD student who identified from various different sampling in Mauna Loa Observatory in Hawaii that there was an increase, as I say, in carbon dioxide concentrations. Another 10 years passed. Don't panic, nothing to worry about, another 10 years passed. And then we get through to Manabe and Weatherall, who started to model the effect that carbon dioxide would have on global conditions. They postulated possibly a 2-degree increase in global temperatures, and they started to do some serious modeling utilizing supercomputers. And by the way, supercomputers are a major aspect to this because climate is insanely complex to model mathematically, and consequently it takes a lot of computing power. By 1985, we got some additional different sources of evidence. This came from ice cores, primarily in the North Pole, where you basically put a big hole into the Greenland ice sheet. You pull out ice cores, and now you can actually got frozen little sections, like again with the same idea as the wood from dendrochronology. You've got little year after year after year of changes in atmospheric composition. And so they did some research at that point, and they've gone down as far as 150,000 years, and they've found quite consistently that over the last couple of hundred years we've seen increases in carbon dioxide concentrations. Needless to say, nothing happened for a couple of years. And then we started to think in terms of, well, hang on a minute, what's going to happen long term? That's the point in 1987, 88, where we started to see the things like the Brundtland Commission and the the introduction rather, of a concept known as sustainability, a word that you've all heard many times, correct? Yes? Okay. You can tell your age by what words you use. Sustainability became the sexy word of the late 1980s. Okay, that was sexy in climate change terms. Now we don't talk about sustainability, we talk about resilience. Yeah, because it's not necessarily just about maintaining production in its current rate, it's actually being able to cope with change. And that requires a different thing rather than just continued outcomes as they currently exist. A little bit further forward, and we start getting to the point where we sort of get into the, quotes, modern age, as it were. In 1994, we got to a point, 1994, we got to the point where we recognized the fact that we're going to have to do something about this and commit ourselves to change. 95, Kyoto Protocols were signed by Barack Obama, or I think it was, Bill Clinton, I think it was, back at the time. And then subsequently the Paris Climate Accord in 2016. The thing about the Paris Climate Accord was it actually committed the entirety of the planet, pretty much 200 countries, 197 countries, pretty much everybody, to say, what we're going to do is we're going to legally commit ourselves to reducing carbon dioxide concentrations and all other gases related to climate change. One of the things that happened in New Zealand, just for a giggles moment, is we have an awful lot of cows and sheep in New Zealand. Did you know this? So we've got 5.5 million people, we've got 38 million sheep, and we've got 12.5 million cows. Now the good news is we've got no snakes. Australia's got all the snakes, we've got no snakes. And it has to be said, if the cows and the sheep ganged up on the humans, we've got a major problem because they outnumber us a lot. Okay, so we try not to annoy the cows and the sheep. However, one of the things that occurred in New Zealand, it came political football, was the fact that all of a sudden the methane coming from cows, you know, methane, type of methane. Yes, so if you actually Google the phrase cow farts, sadly, the first country that will be mentioned is New Zealand. And this is true. We have an ongoing issue with cow farts that we're now moderating with changing the actual dietary behavior of cows. Isn't that nice? You know, see, we are working on the cow's waistline, which I think is, I'm quite proud of. Anyway, it's a whole new world. Anyway, long story short, 2016, we committed ourselves to reducing climate change through reductions in the utilization of hydrocarbon fuels and also production of climate change related gases such as carbon dioxide and methane. Okay? And that is a global thing. Now it's a big deal because when you commit yourself in that way, there are going to be penalties associated with it. It's actually going to cost us money if we fail to deliver on this. Oh, and by the way, ladies and gents, it's the same with you guys as well. You know, so the whole issue with, for example, the introduction of compressed natural gas as a fuel for tuk-tuks and all this sort of stuff, you know, that's just part of that package, and you're going to have to ultimately make changes yourself in the same way that we are. You know, we have a population of 5.5 million people as a nation. You guys have got 1.5 billion people. In sort of Indian terms, New Zealand is a village, right? We're a tiny place. We can't impact things anywhere near as much as you guys can. The other thing is we also actually have as our principal source of power generation 2 fuels, technically 3 fuels. Wind power, hydro schemes, as in water power, right? And one of the things you've probably never heard of is geothermal. So we actually inject water into the ground where it gets hot because we've got volcanoes and things, and then we tap that coming off. So we're actually highly sustainable in terms of power generation, but we have the issue of the cow farts, obviously, I don't want to get into. It's quite embarrassing talking about cow farts, I'm just saying. Anyway, moving on. What does that mean as far as New Zealand is concerned? What we had to do is figure out a way dealing with this going forward. And actually the principal way in which New Zealand is going to deal with this problem going forward is through a policy document called Adapt and Thrive. Now, if you're feeling keen, you can Google the phrase Adapt and Thrive New Zealand, and you can get the report. It's 285 pages of finely crafted stuff that I had to read. But the basic premise is this. We're going to move cities and towns away from the ocean. We're going to move inland. We're going to get to the point where we're actually replacing infrastructure and moving away from the affected areas. That's a massive undertaking, hundreds of billions of dollars worth of undertaking for a very small economy. And that's how we're doing business here. Now, you know, what we're going to see in the future, on the basis of all the stuff I've just outlined here, we're going to see increased sea level rises. What we're going to see is higher storm surges. We're going to see more energetic weather events. You guys collectively will be familiar with that minor issue known as monsoon, right? I was being ironic. Now, the minor issue of the monsoon, in your own experience, is it getting worse? Is it getting more dramatic, more energetic, higher winds? bigger rainfalls? Yeah, and that's to be expected as temperatures increase and as water levels rise. The amount of energy that's picked up by the storms comes directly from the seawater. That in turn generates all these highly energetic events. Ladies and gents, we're going to see more of it. This is inevitable. In addition to which, we've got critical infrastructure at risk. We've got roads, a lot of roads. We've got sewage. We've got water supply. We've got stormwater reticulation. We've got power transfer. All of these things are going to be impacted, whether you recognize it or not. These are massive infrastructural loads that we're going to have to deal with going forward. And we're already starting to plan for this, and I'm going to show you some of the examples of this. And this is going to be ongoing. We're also going to see more unstable weather systems. So, for example, in my part of the world, down in New Zealand, we get something called El Nino. El Nino is a reversal of standard Pacific-driven, or South Pacific-driven air currents. Now, El Nino used to take place every 7 years. Now it's taking place every 2, and then it's happening two years on the run. We have El Nino and La Nina, which follows on immediately afterwards. This causes immense difficulties associated with rainfall and so on. New Zealand, for us, you know, we're the land of the long white cloud. Literally, Aotearoa, which is the name New Zealand, means land of the long white cloud. This is something we rely on our rainfall. We actually export our rainfall dehydrated. It's just seen the fact, what? I'll explain. We convert our surplus rainfall into a couple of things, the most important being cows. Cows convert grass into milk. We export milk to the world. We export milk dehydrated. We export 40% of global dried milk powder coming from a tiny little country, Speck, in the bottom right-hand corner of the world. You can see it? Right, that's what we do, and we do it dehydrated. So when I say we export water dehydrated, that's why. Okay, so we've got a whole bunch of stuff to be able to plan for and think for the future, and we need engineers and architects who have the vision and foresight to be able to deal with that. Anyway, going forward, do we have a lot of evidence to be able to demonstrate that this is the way that it's going forward? And the answer is yes, we do. We have got a lot, but it's mainly circumstantial. And the reason why I say it's circumstantial is the linkage that we have is analogous between the linkage that we have in our mind between smoking and lung cancer, or smoking and heart disease. The actual causal mechanism is shrouded in a little bit of mystery, but we see it so frequently the statistics can't be denied. I love this photo, by the way. I have 2 hobbies, alcohol and swimming with dolphins. Spoiler alert, it's not a dolphin. Okay. But we see clear trend lines between the two issues of carbon dioxide development and global temperature changes. If we look fundamentally, we can actually deal with this, and we can actually plot stuff. We've been taking readings in climate science for many, many years. Now, this particular graph shows a pretty much straight line growth in underlying temperatures between the 1880s and the year 2020. And you think, case closed, right? The only slight problem is that the numbers at this end don't indicate the fact that during that latter period, the 1880s and so on, there was actually what was referred to as a mini ice age in Europe. So again, this indicates the nature of how climate science is being weaponized or shall we say biased against you, because you're being told only a little thing, a little sort of snippet. And we don't act, if I stretch this back 60 million years to the point where we had T-Rex on the Earth, okay, go back to the Cretaceous period or Jurassic period or whatever, we've all seen Jurassic Park. That's it. That is my T-Rex impression. You're not going to get a better one than that. It's always the guy who goes to the bar and doesn't want to pay. Arms are too short to get the hands in the pockets, right? It's the T-Rex effect, we call it. Anyway, we've got this as an ongoing thing. But if I go back in time to the point where I go far enough back in time, we go back to that period, 60 million years ago, then average temperatures on the planet were substantially higher than they are now, right? So there's various different measures that are taking place, various different technologies that are taking place. Let's face it, T-Rex wasn't driving around in a V8. You know, they weren't driving around in a big car or a tank. You know, they were footbound, right? Anyway, back to the story. So if we start plotting what's actually taking place, we actually see quite substantial differences around the world. The red areas indicate areas where temperatures are increasing, the blue areas where they're cold and reducing, right? So we don't even have a comprehensive picture where it's identical around the world. Here's an example of some of the problems that we have as well. We get cyclic behaviors that are taking place. Now this graph here actually goes back from the modern day where we see current carbon dioxide concentrations sitting at around about 400 parts per million, which has increased since the 1700s, where it used to be about 350 parts per million. So we're going up, right? However, we see cyclic change in the history, going back, in this instance, for about 400,000 years. So again, what's driving that? The answer is volcanic behaviors. So any large volcanic eruption generates huge amounts of carbon dioxide. Last time I checked, volcanoes hadn't been switched off. Therefore, we still have this as an ongoing issue. So we're still going to have to be able to cope with change. Just as an interesting aside, go back 10,500, 11,000 years, we had something called the Younger Dryas. What's the Younger Dryas? It was a mini ice age that we had, okay? The Younger Dryas saw temperatures increase substantially over a very short period of time. In a 3-year period, the global sea level rise took place of over 400 feet. 400 feet. At this time in history, India, southern India was connected to Sri Lanka. The entirety of Indonesia was actually a major plateau with hills in it. There was a link between northern Australia and Indonesia. There was a link between Europe and the UK. You know, we had all of that taking place, and over a 3-year period, there was a catastrophic increase in sea level rises, which saw, as I say, 400 feet, over 100 meters of rise in a 3-year period. So when you think about all the legends that you have in your own cultural history about the periods when there was a major storm and, you know, the likes of Noah's Ark came along and took all the animals and all that sort of stuff, they are all of those, there are about 400 different legends globally where that takes place. So we, as a culture, and I'm talking about all locations around the world, have exactly the same experience of global catastrophic sea level rises that took place during the Younger Dryas period of about 11,000 years ago. But again, if I go back in history, 60 million years, bearing in mind we're talking about today, we have 400 parts per million, or about 0.04 of a percentage point. Currently, as the amount of carbon dioxide in the atmosphere. What was the carbon dioxide level during Jurassic period, during T-Rex times? Anybody? Here's a fun fact. No? See that cyclic behavior? Forget that. It was 2,000 parts per million, 5 times higher than it is today. And again, this all comes from the volcanic action that was taking place at the time. There is a major volcanic rupture that took place close to here, actually, to the north, where you've got all of the mountains heading up towards Pune. Yep. All those mountains came about as a single geological event where it was literally an earth rupture of a couple of 100 kilometers long, and it just spewed out a lot of lava for a long period of time. Anyway, interesting, eh? Today is a day at school, a little bit of history, a little bit of archaeology, a little bit of paleontology. Anyway, underlying all this, we've got sea level rises taking place, which are seeing, over the last 100 years or so, we've seen about 150 mil, about 6 inches of sea level rise. That's a significant effect. But going forward, as we start to see what's going to happen in the future, we're actually looking at a high worst case scenario of 3.5 to 5.5 degrees centigrade to a best case scenario of actually temperatures dropping by a couple of degrees, and an expected case of probably 2.5 to 3, which in turn leads to quite substantial increases in sea level rises. We're going to see something between 0.5 meter and 2 meters. Well, I'm here to tell you, ladies and gents, if we see a 1 meter or even a 0.5 meter, what do you think is going to happen in somewhere like Bangladesh, for example, where a bulk of the country is actually literally within 1.5 meters of sea level, current sea level? Where do you think all the people who are going to be then out of their where they live, where are they going to come? You think that might be a little bit of a social problem for you. But the point is, ladies and gents, it's coming here. It's coming here, it's not just elsewhere. It comes everywhere. Even 10 centimeters in New Zealand, what we're going to see as a result of 10 centimeters, just this, 10 centimeters, we're going to lose about 130 kilometers of road. We're going to lose maybe 360 kilometers of buried pipes. If you start shutting down sewage pipes or whatever, what's the first thing that happens associated with public health? You're going to start seeing all of the bad news bears type of stuff happening with public health. We're going to lose water supply, we're going to lose stormwater reticulation, we're going to lose at least 45 square kilometers of real estate that's productive land at the moment. That's just for New Zealand. If you look at who's going to be affected globally, because of the specific geology associated with this part of the world, the biggest single impacted area is going to be South Asia. And that, ladies and gents, is a scary thought right there. We've got problems, but we're down in the bottom right-hand corner there. You can hardly see us on the map. We're tiny problems. Here we've got big problems. To put it in context, what does it mean about New Zealand? Well, if you've never seen New Zealand before, we're basically 2 big islands. Anywhere that's purple on the top map, that's low-lying. It's probably within 3 or 4 meters of sea level. That's where the bulk of the people live. Of course. Let's not make it easy for ourselves, right? Just for interest's sake, if you ever want to come on holiday or study, if you want to see what New Zealand's really about, see the bottom map? All the green areas, that has a population density, and then that, by the way, that's 98% of the real estate of the country. 98% of the real estate of the country has a population density less than 1 per square kilometer. One person per square kilometer. So there's plenty of space. Bring your friends. We have lots of real estate to deal with. Anyway, but our problem is, fundamentally, we live in all the flat bits that are close to the ocean. So we've got a disproportionate problem because everybody lives in the areas that are going to be maximally affected, which is a major problem. If we take Auckland, for example, all the light blue, obviously the light blue is water, but all the lighter blue, sort of light purple, that's less than a meter or so between the ocean and the height of the ground. There's an awful lot of reclaimed land. So you can see in Auckland we're going to lose a huge amount of the real estate for around the coast. This is Wellington. Dependent on how much real estate gets or how high the water comes, we're going to lose anywhere where you can see red or the yellowy sort of area. That's all going to be subject to inundation as well, and it's obviously it's where everybody actually lives. It takes a different perspective. This is actually a map around Christchurch, where we had the earthquake in 2011. In this particular instance, all the spots that you can see, where it says electricity, water supply, wastewater, they're all pumping stations. They all sit in the flat area around the main floodplain close to Christchurch. So there's something like 300 different sites that are all going to be subject to inundation that need replacing. So even at the lowest level, we're talking about the requirement to replace key infrastructure to keep everything operational. As soon as pumping stations go down, you've got a major problem. First thing that happens when it comes to dealing with disaster is actually to set up the scenario where electricity is reinstated and pumping stations can function again. You will be amazed by how much damage is created just by electricity being shut down so pumping stations fail to pump. So, as I alluded to before, our key policy is to retreat. We're going to have to replace about 300,000 homes. We're looking at something like $100 billion worth of property value. We're going to have to work on things like, for example, stormwater defenses, flood defenses, and so forth. It's going to be an ongoing exercise, and what that means for people who want to come to New Zealand to potentially live, work, and study, or study, work, and live, whatever order, is that there's a huge opportunity for anybody who wants to get involved in infrastructural development, because that's where we're going to be focusing a whole bunch of our effort going forward over the next few years. What does it mean in terms of infrastructure and that sort of stuff going forward? A whole bunch of technologies we're increasingly dealing with. So here, for example, cramp in my hand. Here, for example, this picture on the right-hand side, you're looking at a 100-year weather event. This took place, it was called Cyclone Gabrielle in the beginning of 2023. That was a 100-year weather event. We've had 3 subsequent 100-year weather events that took place all in the same 3 years. Now I'm not great with statistics, but I reckon a 100-year weather event should happen on average once every 100 years. Am I right? No, I'm sure I'm right? And yet we've had 3 in 3 years. And that's an increasing behavior. And the same is happening globally. We're having a total change in the way in which weather systems occur. Anyway, this occurred. Now here's the fun part. This area in Auckland is actually one of the principal redevelopment areas and expansion areas for new housing developments. So we are building our future housing in all the areas that are getting affected by flooding. And it's an ongoing issue. And by the way, this happens globally throughout the rest of the world, all the way through the developed world. You'll find peripheral housing development zones in floodplains on river valleys in the cities that we have. Anywho, the effect that it had for us was dramatic, because not only we had the flooding, but we also had massive geotechnical events that took place, major hillside collapses and so forth. If you soak a bit of real estate in enough water, it becomes unstable. It is no longer solid, it is now semi-liquid, and all of a sudden you've got a problem. So you can build where you like, ladies and gents, doesn't matter. Nature has an amazing ability to hold the draw card, and all of a sudden you've got a problem. You know, looking forward, we're going to have to change the way in how we invest, where we invest, even how we generate things like insurance to be able to recover your costs if your house gets wrecked as a result of weather events. We need to figure out a plan B dealing with all this. The way in which we're doing it at the moment in New Zealand is by adopting various different technologies, all of which have a role to play. So for example, we take classic, you guys as architects, you'll be familiar with the concept of green roofs, right? Aren't green roofs lovely? They're pretty. Oh look, we've got flowers on the roof, lovely. There is a very much more pragmatic engineering requirement. What it comes down to is slowing down stormwater dissipation, and what we end up with is trying to reduce the stormwater pulse in the stormwater reticulation system. This is an engineering outcome. So what we're trying to do is reduce that stormwater pulse and slow the water release down. So one of the ways we do it is with a green roof, so we absorb stuff into the roof. The problem is structural, because obviously you put enough water on the roof, then all of a sudden you've now got 30 tons on the roof when it didn't have a load before. Now you've got a problem, right? But again, it's a useful tool. Probably more useful in New Zealand is this, the bottom example, which is a stormwater detention system. Now, stormwater detention systems are really useful, particularly in new builds. So we're we're increasingly specifying new builds with stormwater detention, again to slow down water release into the stormwater reticulation system. Next one we use is putting things on piles. This is classic in sort of areas which are subject to flooding as a result of cyclonic action, for example. The idea here is if we take away the walls around the base of a building, we reduce hydrostatic pressure. Hydrostatic pressure is literally the water that's on the exterior trying to get into the interior. Now, there's two things that happen. One is about buoyancy. The house starts to float if you keep all the water out. But the other one is literally the fact that you're seeking to reduce that lateral pressure, which reduces the engineering component. So we stick houses on piles. And it's very common to see in New Zealand, you know, if I leave for work at 5 o'clock in the morning, which I normally do, I will meet a house coming the other way down the main road. There's a house coming at you. It's scary, let me tell you. They don't have any lights on them. Very scary. They don't signal. It's really scary. Anyway, but we see this all the time because we have removable houses working on basis of piles in that way. Another thing we use is something called wet flood proofing. This is where we actually look at ways and means of allowing water to actually get into the basement area of houses, again, rather than creating the hydrostatic pressure on the peripheral walls. So it's about equalizing that hydrostatic pressure inside and outside. In the same way, if you drive a car into a river, then what you're supposed to do is open a window so that the hydrostatic pressure equalizes so that you can open the door, right? Same sort of concept here. Obviously, there's the traditional sort of dry flood proofing where you just keep you create a levee or some sort of artificial barrier, or just something simple like sandbags work, or steel shutters into a wall. Again, all works. Anything to keep the immediate effects of the flooding at bay and allow the water levels to drop. Other things we can do, we can pipe stuff underneath the foundations, such as this, sub-slab drainage systems. And then we have the classic of levees. Now, these are the sorts of things that didn't work so well in New Orleans back in the day when the levees broke and everybody got flooded out in the central city. But the bottom one there is actually from New Zealand. This is in a flood valley where we've actually built a berm around the farmhouse, and it keeps everything at bay. Anything to keep the water out just whilst the water hits peak level and then drops. Anyway, so there's a range of different technologies we're adopting, and these are what's being taught to architects and engineers in our country to be able to make a difference in the world going forward. Anyway, what does this mean ultimately? We don't seem to learn. At the moment, we're carrying on consenting things. In fairness, there was a change in the law last week, and we've just changed the requirements as far as consenting is concerned. So we're actually no longer building in these areas, because obviously councils are consenting properties to be built at the risk of the owners. And obviously that is not ethical to do going forward, so we're changing the laws. But what I'd just quickly say is, what I've outlined just here is an awful lot of different content. I've given you an awful lot of information. I'm covering an awful lot of different scenarios. It's a huge issue, ladies and gents. It's going to affect you. It's not going to affect me, because by the time all of this gets to its worth, I'll have dropped off the perch and I'll be somewhere else doing something else. Okay, but it's going to be about you guys collectively making a difference in the world. Right at the beginning of this presentation, I asked the question, what do you want to do? Do you want to make a noise, or do you want to make a difference? You want to make a difference, right? Ladies and gents, you're going to be dealing with this going forward. It's going to be up to you. You're going to be the ones we're relying on to make a difference in this world, either in my country or in this country. All the issues I've just raised are not going away. Doesn't matter how much you want it not to be true, it's true. This is what's happening. And my issue as an engineer are, fine, we accept it's true. Let's do something about it. What are we going to prioritize building? What are we doing first? And that's the way it has to be. It's going to change the way in which we own houses. It's going to change the way in which we develop infrastructure. It's going to change the materials we use. It's going to change the designs we use. It's going to change the technologies we use. And you need to be live to it, because the ways that historically we use things are not going to be the way that in the future we're going to be using things. That's just how it is. Ladies and gents, thanks for your attention. I hope I've not bored you too much. Most of you are still awake. This is a good sign. I'll happily take any questions if you have them now. Are you going to ask a question, or are you just going to pretend to ask a question? No questions.
Yeah, I think the questions would be difficult because yours was more informative. It was all facts, figures. But how considering New Zealand is an island in that sense, how much of a water elevation are you all expecting, or how much land are you all expecting to lose out in that sense?
Worst case, I think we're going to see several hundred square kilometers in low-lying areas, particularly highly productive dairy areas, like in, for example, the Thames Valley up to the northeastern quadrant of North Island. Yeah, so there's quite a lot there. We have some interesting dynamics though, because at the same time as water's going up, also some of the land is going up because there's a magma chamber underneath which is actually growing. So we're waiting to see which is going to get there first. But yeah, it's going to be several hundred square kilometers, I would imagine.
Okay, so we are in that sense really worrisome. We are, because we are so very, with a coastline so large, we are really worrisome.
Well,
equally.
as I look about, I mean, I was actually down in Kochi just recently, and around Kochi and around Chennai where I was as well. You know, got massive, massive, massive low-lying areas. And the thing is, with all of this stuff, it's not the initial effect. It's the residual effect. It's too complicated. So what happens if you get inundation of a productive area, let's say, of rice paddy that produces rice for people to eat? What happens if it gets inundated by the ocean? Does it kill everything? Well, the answer is not immediately. However, what immediately happens is that the productive capacity of rice production goes down dramatically. So instead of having total starvation and nothing grows, no. Everything gets depressed, and it does it on a periodic basis, and it gradually, the fertility of the land gradually goes down. As the fertility goes down, increasingly it becomes unmanageable and uncultivatable. Increasingly it therefore becomes desert. Increasingly therefore it's out of production, and it's out of production permanently. What does that mean we have to do going forward? What it means we have to do is introduce, for example, salt-tolerant rice strains. Now, when in the history of any architect ever have you ever considered the need to think in terms of salt-tolerant rice strains for the future of the sustainability of your environment? And the answer is you don't, because it's a complex issue. In fact, you've all heard of the concept of a wicked problem, yeah, where you've got multiple difficult problems. Well, let's go beyond wicked. Let's say fiendish problem, because what you've got is multiple wicked problems. And this is getting to the point where it is absolutely crazily difficult to be able to model it, crazy difficult to be able to plan for it, crazy difficult to be able to design for it. And these are major issues for you guys collectively. You guys collectively are going to be using the sort of tools which ultimately are going to be able to make this happen. Think about the utilization, for example, of AI and all that sort of stuff to be able to consider multiple different, variable optimizations. That's what you're going to be using to deal with relatively basic problems, okay? It's going to be a big issue, ladies and gents. And it's not going to get any easier. It doesn't get any simpler.
Yeah, like I think the first example, first instances will be that you lose all your freshwater sources like wells. Wells get they get salinated first.
Yeah.
So, but naturally your water sources dry out.
Yeah, and then you're going to have to pipe it in from outside, or you're going to have to truck it in from outside, which generates increasing amounts of carbon dioxide development related to the trucking process, and on and on and on. The problem fundamentally, ladies and gents, is that these issues they are not soluble by yourself. Okay, so you know, everybody thinks they can solve the world. They can't. In the future, you're going to have to deal with architects, obviously yourselves, but engineers, planners, those who are dealing with ecology, those who are dealing with environmental engineering generally, to come up with integrative solutions. It's just not monodimensional problems, it's multidimensional. Okay.
I do not know if you're aware that our extensive infrastructure is now being laid entirely along the coast. So crores of infrastructure planning are the new coastal roads that are going to wrap around entire Mumbai and Maharashtra.
Yeah.
And in that sense, we're going to lose all of that investment in some years.
It has the potential. It just depends on whether or not they've been designed for being able to cope with this sort of stuff. And I fear, when you deal with infrastructural development, a key problem that you have is that most politicians, they are interested in the first instance in putting the infrastructure in place. What that means from a construction management perspective is that the biggest single dimension is the cost dimension associated with the solution. Therefore, it's acquisitional cost. Through life cost is not evaluated because the biggest single issue is getting the infrastructure in place. Through life cost is what we're talking about at this instance, and that becomes a harder conversation to have. So for 100 billion rupees, for example, you get this. However, to make it last longer, you're going to have to spend 200 billion rupees. That's a harder ask. Yes, but what happens if the sea levels don't rise? Well, you wasted the money, you know. And that becomes a problem. Politically, it becomes a problem. Yeah, it's a major issue.
Particularly when you're reclaiming land. Yeah. Thank you. Anybody else would like to ask anything in particular? Yeah, the final year students. Yeah.
Hello, sir. I'm Aditya. So I want to ask, as architects, how much should we be involved in policy recommendations about market mechanisms, about biodiversity resilience, because we are going to design at these places, and how much should we balance both our design ideologies and these built environment aspects?
Geez, how long have we got? Okay, well, I'll put it to you like this. When you go and you look at any infrastructure, it doesn't matter what it is. You know, you guys as architects, you know, I could pretty much tell you, dependent on which city you decided was your favorite city, where you would want to go and what buildings you would want to photograph. Now, the reason why I say this is because I do the same, right, as a building person. Taking sexy photographs of buildings, that's what we do, yeah? So if I went to Barcelona, I'd be photographing Sagrada Familia, I'd be looking at Gaudi's work. If I went to New York, I would possibly be going to the Guggenheim Museum, for example. I would possibly be going to the Chrysler building, those sorts of things. We all know on the basis of this, right? Because we appreciate architecture. Thing with it, though, is that what we very often don't appreciate is what the most important construction material in the world is. Anybody want to guess what the most important construction material in the world is? What's the most important construction material? Sorry? So we've got maybe mortar or concrete down here. Anybody want to go beyond that? Steel, glass. Wow. You're all wrong. Fundamentally, you're all wrong. It doesn't matter. The most important construction material in the world is money. You can build anything you want. You want a 10-kilometer long bridge in gold? No problem. What's your budget? Okay? It literally comes down to that. So what we do is we spend an awful lot of time becoming hugely influenced by the aesthetic and the engineering efficiency of a structure and what have you. And if you look at any of Gaudi's work, as for instance, you know, some of the organic curves and all the rest of it that Gaudi incorporated into his build, brilliant, massive, genius, amazing guy. I've been to that particular Sagrada Familia several times, and I've been to pretty much every Gaudi location throughout Barcelona. Well worthwhile, go there. However, the issue is not about the absolute efficiency of the design. It's not about the elegance of the design. It's not about the aesthetic of the design. It's about being able to achieve all these elegant, aesthetic, efficient outcomes and doing it in a way which you can afford to do. So when we talk about balance, the only thing I can say to you guys collectively is if you want to be the best architect you can be is to have a very clear understanding of that efficiency related to budget. That means you're going to have to probably work closely with a construction manager or, you know, quantity surveyor or whatever it may be. But doing that, because that is how a couple of things happen. One, you get your design built, right, which is good. But two, you do it sustainably because it's actually about the money to be able to do that again. Going back to the scenario I gave, you know, creating that efficient flood management policy that we just described to deal with a bit of infrastructure of $100 billion. If you can do it, 100 billion rupees, if you can do it in $100 billion and you've got money left over, that means you can do more with the rest. Unfortunately, I've met with a lot of architects over the years, and the one thing you never tell an architect is that there's a contingency fund, because what the architect will tend to do is try to spend that on some more pretty things. Right? You know you will, because it improves the aesthetic, right? But that's what we have to do, ladies and gents. And it's literally about that pragmatic outcome that's so critically important for the future. Good question. Good God, how long am I supposed to be here? Can we get away? You know when we ask for questions, I'll let you into a secret. We're joking. We don't want questions. What we want to do is say, thank you. Thank you. We're going. Have a nice day. Because that's how we work. But no, really good question. Thanks for your input there. Are we there yet? Yeah, thank you. No problem at all. Thank you very much for your time, and well done.
Let's give a big hand of applause to Professor John Tukey. I didn't expect him to be that flamboyant, but then...
Look, it's just a blue shirt. What do you mean flamboyant?
I was to wear a coat to receive him, and thank God I forgot it in the car myself. But then, thank you, sir, for being here. First of all, I should thank IDP. Yeah, Sunil particularly. Thank you, Sunil, for coming to us. Sunil's one of his nephew studies with us in the interior department, and so Sunil from IDP thought it befitting to get to approach us and tell us that Professor Tukey is going to be here. And Professor Tukey has had students from Aditya at his place, and he could immediately recognize our logo and says that we've had some bright kids there. Yeah, in the future, yeah, there are people who are doing well, studying masters all across the globe. Now with it becoming increasingly difficult to go to the US, and yeah, the world is shrinking in that sense. I thank Professor Tukey for being here. He's brought harsh reality to our forefront. Maybe the harsh reality is great opportunities for you. Yeah.